This lecture talks about some connections between linearly independent vectors and linear systems. Well, let's consider a set of vectors in Rn, let's say A1, A2 to An, be column vectors of a matrix A, and then a set of scalars, which are just constants, right? x1, x2 to xn, be a solution to the system Ax equals to B. Well, let's remind us that the system Ax equals to B can be rewritten as B as a linear combinations of A1, A2 to An, where x1, x2 to xn are the weights. All right, so the first connection is if the set of vector A1, A2 to An are linearly independent, then the system Ax equals to 0 has only trivial solution, which is 0 as a solutions. Then by the theorem 1.5.2, A is non-singular. Again, if A1, A2 to An are linearly independent, then A is non-singular. Also, the system, the homogeneous system Ax equal to 0 has only trivial solution. On the other hand, if the set of vectors A1, A2 to An are linearly dependent, then the system, the homogeneous system, has non-trivial solutions, which implies that A is singular. Okay. And the second connection is if the vector B is in the span of A1, A2 to An, and then A1, A2 to An are linearly independent, then the system Ax equals to B, this is non-homogeneous system, has a unique solutions. In other words, there's a unique set of x1, x2 to xn, which are scalars in these situations here, such that is unique set, such that B is a linear combinations of A1, A2 to An. Again, one, we look at a set of vectors, right, in terms of linear independence and make a connection between the set of linear independent vectors to a homogeneous system, right? If a set of vectors are linearly independent, then the system Ax equals to 0 has only trivial solution. By theorem 1.5.2, A is non-singular. Again, A1, A2 to An are the vectors in Rn, and these are the column vectors of the matrix A. Okay, so linearly independent with non-singular or singular matrices. Second, if you have a vector that is in the span of A1, A2 to An, and also this set of vectors is linearly independent, then the system Ax equals to B has a unique solution. There's two conditions that will give you a unique solutions, right? First, B is in the span of all the column vectors. Second, all the column vectors are linearly independent, then you have a unique solution for the system Ax equals to B. Okay. Well, let's look at an example here. Let the set of vectors 2, 1, -2, 3, 2, -2, 2, 0, 2, 2, 0 are the column vectors of the matrix A. And these vectors here are in R3, as we know, right? So the first question is, does the system, homogeneous system Ax equals to 0 have non-trivial solutions? Well, if we want to know, we should put these column vectors in a matrix. Okay. And we augment it with the 0 vector. Okay, and then I want to reduce this matrix. First, I want to move the second row to the top. So then it's going to be the pivot row, right? And then I do some row operations like row 2 minus 2 row 1, and row 3 is row 3 plus 2 row 1. And then I will have 1, 0, 2, 0, 3 minus 2, 4 is negative 1, 2 minus 4 is negative 2, see 0 here, negative 2 plus 2 is 0, negative 2 plus 4 is 2, 0 plus 4 is going to be 4, 0. And the next one is I just need to take care of the row 3, make this 0, it's going to be row 3 plus 2 row 2. And then you have 1, 2, 2, 0, negative 1, negative 2, stay the same, 0, so it should be 0, 4, plus 2, negative 4 should be 0. So at this point, we know that this system AX equals to 0 has non-trivial solution because you have a free variable. Okay, so then this question is yes. It has non-zero solutions, non-trivial solution because it has a free variable. Okay. Well, then the next question is A non-singular? Well, based on these two theorems, if A is singular, if A is non-singular, then the system has only trivial solutions. But in this case, my system has a non-trivial solution. That means A is not singular. No, because the system AX equals to 0 has non-trivial solutions. Great. So that means A is singular. Okay. So if A is singular, are these vectors dependent, linearly dependent? Since A is singular, then using this theorem up here, if A is singular, then we have dependent vectors. These three vectors are linearly dependent. So you say yes. As you can see that if you have a set of vectors forming a matrix, right, and you look at this system here, and if the homogeneous system has non-trivial solution, that means the matrix A is singular. If the matrix A is singular, that means the three column vectors are linearly dependent, and you'll find how they depend on each other on the next sections when we talk about column vectors, column space, and the row space of the matrix. All right, here you go. This is some connections between linear independencies with linear systems.